Hello everyone and welcome to our channel Mootechie. It's great to have you with us. Today we're diving into a fascinating topic from the world of food science, beer processing technology. Coming up, we have our learning objectives. By the end of this lecture, you should be able to A. Identify the major raw materials and ingredients of the brewing process, along with their respective contributions. B. Understand which parameters and operations are important for the production of stable beer. C. And finally, explain the entire production process of beer from start to finish. Following this, let's begin with a brief introduction. Alcoholic beverages are essentially flavored solutions of ethanol derived from numerous substrates. For example, we have grains, as in beer, grapes and other fruits, as in wine, and really any other carbohydrate source, as we see in distilled spirits. The magic behind this is fermentation, which is carried out by species of Saccharomyces yeast. Sometimes, this yeast is presented naturally, like on the skins of grapes in winemaking. Moving forward, let's talk about beer production itself. Beer is the most widely consumed alcoholic beverage in the world, and incredibly, it's the third most popular drink overall after water and tea. Now, what goes into beer? The essential ingredients. Most beer is made from 4 key components. I. Water. 2. Barley or malt. 2. Hops IV. And yeast. Sometimes, other carbohydrate sources called adjuncts are used, such as cereals, whether malted or unmalted, starch or sugar syrups. Let's continue on this topic. Not only do the ingredients differ, but they can also be used in numerous combinations with different brewing operations. This is why beers can vary so much. They can differ in alcohol content, typically from 4% to 6% by volume, bitterness, pH, turbidity, color, and most importantly, flavor. Now let's understand these ingredients more clearly, starting with water. Water makes up a massive 90 to 95% of the total ingredients in beer. So its composition is critical. Basically, water affects the beer in 3 main ways. First, it affects the pH of the beer, which influences how the beer flavors are expressed to your palate. Second, it provides a kind of seasoning, from the sulfate to chloride ratio. Sulfate can enhance the hop character and contribute to a dry finish, while chloride can provide a rounder, fuller, sweeter character. And third, it can cause off flavors from chlorine or other contaminants. The various uses of water in a brewery may require different compositions or treatments appropriate to their specific functions. Next up is barley malt, the second most important ingredient. Barley is considered the perfect grain for making beer, and for several key reasons. A. It has a sizable amount of protein which is necessary for giving the beer body and head, though excess might cause cloudiness. B. It has all the enzymes it needs to convert its own starches into sugars. C. And it has a lipid content. Let's continue with the advantages of barley. D. It has a high amount of starch per grain, which means more sugars, leading to more alcohol in the finished product. E. And wonderfully, it has a removable husk, which forms a natural filter bed during the lautering stage of brewing. No other grain has this ideal composition, which truly makes barley the best grain for the job. So what happens to the barley? It is germinated under controlled conditions to become malt. There are 2 main types of barley: 2-row, which has a smaller husk and is more uniform, and 6-row, which has a larger husk, is less uniform but has an advantage in enzymatic activity. The malt determines the beer's color, texture, foam, stability, and flavor. Sometimes other grains like wheat, rye, oats, sorghum, or millet are used as well. On this slide, we see 2 images labeled 2-row and 6-row, showing the physical difference between the 2 barley types, with the 2-row appearing more slender and uniform. Our third essential ingredient is hops. Hops are the flowers or cones of a plant called Humulus lupulus. They contain 3 important groups of substances: hop resins, which include alpha acids and beta acids, making up 10 to 20% of the hop dry weight. These are responsible for bitterness, taste, and aroma, flavoring agents, and polyphenols. The slide breaks down the specific compounds. For alpha acids we have humulone, columulone, and adhumulone, and for beta acids we have lupulone, colupulone, and adlupulone. And finally, our fourth ingredient, yeast. Most beer is made from one of 2 different yeast types: lager yeast, which is bottom fermenting, known scientifically as Saccharomyces carlsbergensis, and ale yeast, which is top fermenting, known as Saccharomyces cerevisiae*. There are hundreds of strains of these 2 types, and each particular strain will behave somewhat predictably, producing distinctive characters in the beer. Now that we know the ingredients, let's explore the brewing steps themselves, starting with 1. Malting. This is a process of controlled steeping, germination, and killing that transforms the barley into a product that is much more friable, with increased enzyme levels like hemicellulases, proteolytic enzymes, and amylases, and with altered chemical and physical properties. Malt provides carbohydrates, proteins, and lipids. These new enzymes, together with those already present in the grain, start to break down the food reserves of the grain. Let's look at the malting process in more detail. It starts with cleaning the barley. Then steeping gori, where we increase the moisture content to 38%, allowing uniform germination within 14 to 20 hours. Then comes germination. During this physiological process, the nutrients stored in the endosperm are partly consumed and degraded by enzymes. Key parameters here are moisture, temperature, the ratio of air to carbon dioxide, and time. So how do we stop germination? This is achieved by heating or cleaning the grain with hot dry air. This does two things. It stops germination and it dries the malt to preserve it, reducing the moisture content from 40 to 50% down to a storable 3 to 8%. The temperature during cleaning is a careful balance with enzymatic activity. For pale malt, we want good enzymatic activity. For dark malt, we allow for Maillard reactions, like the caramelization of sugars, which gives color, flavor, and aroma to beers like stouts and porters. This balance is very important. The color of your beer is largely derived from the color of the malt. Finally, the roots are removed mechanically, and the malted barley is stored ready for use. Next we have 2. Milling and adjunct use. The grinding of malt is accomplished by using smooth or fluted cast iron rollers. The goal is maximum extraction of sugars during the next step, mashing. After crushing, the grist is separated into 3 main fractions: husks, grits, and flour. Barley malt can also be supplemented with other starch-rich cereals, either malted or raw, for specific purposes like oats, maize, rice, rye, sorghum, or wheat. Why would we use an adjunct? Well, for one or a number of the following reasons. To produce a more stable beer, as they contain less protein. To produce a different flavor. To produce a better beer foam, due to lower fat or lipid levels and different proteins. To improve the ease of processing in the brewhouse. And to produce beer at a lower cost. Now let's get into the heart of the process with 3. Mashing. This is simply the mixing of warm water with the grist in a large vessel known as a mash tun. At this time, dry malt adjuncts may be added. Here, enzymes, especially alpha amylase and beta amylase, break down the starch in the grain and convert it to simple sugars. This process yields the soluble malt extract, which is called wort, a sugar-rich liquid. Let's talk about mashing procedures. There are 2 main types. Infusion mashing, where you mix the malt with the water and heat both together. This is widely used. And decoction mashing, an ancient process used before accurate thermometers, where you take a portion of the mash, boil it, and then reintroduce the boiled content. The objective is the same, to make the enzymes become active. We use specific temperature holds, called enzymatic rests, to get maximum activity, such as the beta, glucanase rest, proteinase rest, and amylase rest. Once mash conversion is completed and the starch has been broken down to sugars, we move to 4. Lautering or wort separation. The principal objectives here are to produce bright, clear wort, and to collect the maximum amount of sugars or extract from the residual solid materials. The wort is obtained in 2 steps. 1. First, lautering of the first wort by filtration. The spent grains left over are often sold for cattle fodder. 2. And second, sparging, which is the leaching of the extract that remains in the spent grains with hot water. Following this we have 5. Wort boiling and hopping. The wort obtained by lautering is boiled in the wort kettle, and during this time hops are added. This process has several crucial functions: evaporation of excessive water to achieve the desired wort concentration, inactivating most of the enzymes, sterilization of the wort, coagulation of the proteins. This flaky precipitate is called the hot break or hot trub. This is important for beer stability and foam, extraction of oils and resins from the hops, enhancing color development, and finally, removing volatile components like sulfur-containing aroma compounds. So what happens to that coagulated material, the trub? It needs to be removed in a vessel called a whirlpool. The hot break are the particles present in the hot boiled wort, and they are quite large, about 20 to 80 μm. But a much finer particle, called the cold break, about 2 μm in size, appears when the wort is cooled below 60 to the power of circ C. This can be a problem by coating the yeast and inhibiting efficient fermentation. Now we need to prepare the wort for its most important transformation. This is 7. Wort cooling and aeration. We cool the wort to the temperature desirable for fermentation before yeast is added. The temperature for fermentation is 9 to 14 to the power of circ C for lager, which is bottom fermentation, and 16 to 26 to the power of circ C for ale, which is top fermentation. We also aerate the wort, providing oxygen for the yeast to complete fermentation consistently. The air or oxygen will dissolve to varying degrees depending on the method of injection, with more finely dispersed bubbles dissolving more efficiently. This brings us to 8. Yeast handling. The inoculum has to satisfy several conditions to be used for fermentation. It should be active and healthy to minimize the lag phase. It should be available in large volume. It should have suitable morphology. It should be free from contamination. And it should retain its product forming capacity. Next is 9. Yeast pitching. This is when we add the yeast to the wort. Contamination of pitching yeast with either bacteria or wild yeast must be minimized, as it will cause undesirable flavors in the beer. Sometimes, holding the pitched wort in a starting tank for up to 24 hours before transfer to the fermenter allows some undesirable solids to be removed by settling or flotation. And now, the star of the show, 10. Fermentation. This is where the yeast converts glucose in the wort to ethyl alcohol and carbon dioxide gas, giving beer its alcohol content and carbonation. But that's not all. Other reaction products include higher aliphatic and aromatic alcohols, esters, organic acids, carbonyl compounds, sulfur-containing compounds, and polyhydric alcohols. All of these are incredibly important for the properties and quality of the resulting beer. Their combined contributions make up the flavor or sadly the off flavor of the beer. Let's understand the effect of pH during fermentation. During the main fermentation, the pH value decreases by about 1 unit because of volatile and non-volatile organic acids. The pH of finished beer ranges from 4.3 to 4.6, and this low pH during storage inhibits bacterial growth. This pH drop also leads to the precipitation of high molecular mass nitrogen compounds, polyphenols, and bitter agents. The result is a decrease in color and a change in the bittering effect. On this slide, we see a graph titled Time of Fermentation vs Parameters. It shows 3 lines tracking sugar, cell number, and pH over time. We can see the sugar level decreases steadily, the cell number of yeast rises and then falls, and the pH drops sharply and then levels off, visually representing these key changes during fermentation. Now let's classify these fermentations. First, A. Ale fermentation. Here, the yeast used rises to the top of the fermenter at the end of fermentation. It uses Saccharomyces cerevisiae at a warmer temperature of 16 to the power of circ C to 26 to the power of circ C. The fermentation is fast and exothermic, so cooling is often applied to maintain a constant temperature. The slide has a graphic comparing lagers and ales. It shows lager yeast at the bottom with a temperature range of 48-58 to the power of circ F or 914 to the power of circ C, and ale yeast at the top with a range of 60-78 to the power of circ F or 1525 to the power of circ C, clearly illustrating the bottom fermenting and top fermenting concepts. Continuing with ales, they are known for yeast-derived flavors like fruity esters and encompass everything that isn't golden and clear. The yeast is cropped or collected early from the vessel to prevent off flavors from yeast autolysis and to provide healthy vital yeast for subsequent fermentations. The graphic is repeated here for emphasis, again showing lager yeast at the bottom and ale yeast at the top with their respective temperature ranges. Now let's look at B, lager fermentation. In this case, the yeast used settles to the bottom of the fermenter. It ferments at a lower temperature, typically 9 to the power of circ C to 14 to the power of circ C. It uses bottom-cropping Saccharomyces pastorianus yeast. This process gives a more explicit taste of the malt and hop, resulting in what we often call a crisp beer, and typically results in yellow beers. The slide once again shows the comparative graphic, with the lager yeast chilling down at the bottom and the ale yeast on top. Coming up, what happens to all that carbon dioxide produced during fermentation? The excess CO_2 is either released to the atmosphere, or it can be collected for use later in the packaging process, or even for carbonating soft drinks. A level of CO_2 remains in the beer to give it its wonderful effervescence. Toward the end of fermentation, as the sugars are depleted, the yeast begins to flocculate or clump together. Brewers check the sugar levels in the wort or beer using a hydrometer or refractometer to monitor this. Once fermentation is complete, we move to 11. Filtration and yeast removal. More powdery yeast strains are best removed by centrifugation or filtration, while highly flocculent strains are more efficiently separated by sedimentation. Generally, clarification is assisted by a so-called filter aid, which keeps an open bed for the beer to flow through while also providing pores that trap solids. A part of the leftover yeast can be recycled from 5 to even 100 times before its viability decreases and contamination becomes a problem. Next is 12. Aging EEC, which refers to flavor maturation. During the next 2 to 6 weeks at a temperature close to zero, precipitation of yeast and other undesirable products occurs. Sometimes caramel may be added to control color, and isomerized hop extracts may be used to control bitterness. During this cold storage, the beer must be carbonated to the desired CO_2 level. For draft beer, it's around 0.48%, for canned beer 0.50%, and for bottled beer 0.55%. The slide has a fun simple graphic showing 3 glasses of beer labeled overcarbonated, perfect CO_2 blend, and undercarbonated, with the middle one being the obvious goal. So why is beer carbonated? It's all about enhancing mouthfeel, flavor, and foam or head. The CO_2 also preserves the beer by reducing its pH. After aging, we have 13. Clarification. This step removes any remaining yeast and suspended particles that form during cold storage or aging. Filtration will produce a bright, sparkling beer that will remain clear throughout its shelf life, provided that stabilization has been correctly applied. For draft beer, pasteurization is also often used. Finally, we reach the last step, 14. Packaging. The packaging of beer can be divided into 2 categories. For bottled or canned beer, packaging includes bottling, crowning, pasteurizing, labeling, and packing. It's noted that brown glass bottles are still the ideal material, as they provide the ultimate protection against UV rays, which can spoil the beer. For keg packaging or draft beer, the process involves keg cleaning, filling, and packing. The next slide simply says, to summarize, which we have effectively been doing throughout this walkthrough. Now, it's important to know what can go wrong. So what are the defects in beer? Deterioration is caused by sunlight, storage at room temperature, shaking of the can, and internal oxidation caused by residual oxygen. A turbidity defect can occur due to unstable protein-tannin complex, or starch. And off flavors can be caused by poor quality ingredients or contact with metals. Finally, let's talk about sustainability with 4. Byproducts and waste. The brewing process is quite efficient at reusing its leftovers. During malting, the rootlets that form on the grain can be collected and used for animal feed. The hops filtered out from the finished wort can be collected and used again as a fertilizer. The residual yeast from brewing is a rich source of B vitamins. It can be used by pharmaceutical companies to make vitamins or drugs, or used as a food additive. And of course, used beer cans and beer bottles are routinely recycled. And that brings us to the end of our lecture on beer processing technology. We've covered everything from the 4 essential ingredients to the intricate steps of brewing, the science of fermentation, and even how the industry manages its byproducts. Thank you.